Hello and welcome. If you're new here, my name is Joe, and I rant about the things that I think we need to do to prepare for the coming effects of climate change. If you've been here before, welcome back. In this video, I'll be discussing what the cause of climate change actually is. So to understand why the climate is changing, or why the globe is warming, we used to call it global warming, but climate change is more accurate because it's not just a temperature change. It's a change in precipitation patterns, which is affecting wildlife, plant life. The whole ecosystem is changing. Climates are changing, but really what's going on is the source of all of this change is that the Earth is getting warmer. So to understand why, you first have to understand where the Earth gets its heat from in the first place. So let's take a look at how solar radiation works and how energy is transmitted from the sun to the Earth, and then what happens to it once it gets here. So here we have the sun and the Earth. This is obviously to scale, and this is to show how electromagnetic radiation, or solar radiation, or what we call sunlight, travels from the sun to the Earth. Now you probably remember from an earth science class or physical science class that once sunlight gets to the Earth, one of three things happens to it. 29% of it is reflected right back out into space. Most of this is done by the atmosphere in the form of clouds, but the surface can reflect some back up into space as well, especially snow and ice. Deserts can to some extent, even the oceans. But anyway, part of the sunlight, exactly 29%, goes back out into space. 23% of it is absorbed by the atmosphere before it even gets to the surface, and then the remaining 48% is absorbed by the surface. It's absorbed by the oceans, it's absorbed by the ground. So these are one of the three things that can happen to sunlight once it gets to the Earth. Now, to understand climate change, or why the Earth is getting warmer, we have to go a lot deeper than this and look at sunlight in terms of what actually makes up the electromagnetic waves that travel from the sun to the Earth. So think of sunlight more of a series of a bunch of waves all overlapped with each other. There's waves, long wavelengths, short wavelengths, a whole range of wavelengths that this radiation has. This will be a lot easier to visualize if I split these out. So again, there's some wavelengths that are really short, some that are really long. Really, to better understand this, I first want to go through a brief explanation of just what is, or what are all the different ranges of electromagnetic radiation. So let's take a look at the electromagnetic spectrum, which the axis at the bottom is using what's called a logarithmic scale. If I used a linear scale, this would never work because the differences in these wavelengths, the orders of magnitude from gamma rays to radio waves, is enormous. This is shown in what's called micrometers. So right in the middle it would be 1 micrometer, and then over on the far left, gamma rays, we're getting into 1/1,000,000th of a micrometer, and then over into up to radio waves, we're getting into 100,000 micrometers. So anyway, there's 7 different types of electromagnetic waves. You have gamma rays, X-rays, ultraviolet waves, visible light, infrared light, microwaves, and radio waves. Now, the type of energy, or electromagnetic energy, that any object emits is affected by the temperature of that object. The higher the temperature, the lower the wavelength of the waves will be that this object emits. Another way to think of it is the smaller the wavelength, the more energy those waves have. And if these waves have more energy, that's indicative of something that has a higher temperature. So if we look at the range of wavelengths that the sun emits and that the Earth emits, this is what it looks like on this particular scale, covering from gamma rays all the way over to radio waves. Now, most of the electromagnetic waves that the sun emits are in what's called the visible spectrum, what we can detect with our eyes. Pretty much all of the radiation that the Earth emits is in the infrared spectrum. Some of the sunlight is coming in at the ultraviolet as well. I mean, there are X-rays that come here. The sun emits radio waves as well. But for all intents and purposes, pretty much all the radiation that makes it out to Earth ranges from ultraviolet to infrared. So let's take a look at just the ultraviolet to infrared range so we can make more sense of this graph. So here we have the radiation as emitted by the sun in terms of what wavelengths it covers, and same thing with the Earth. These are not to scale. Each one is what's called normalized, so that the sun and Earth, we can make easier comparisons between these two graphs. The actual amount of radiation being emitted by the sun is many, many, many times higher than what's coming out of the Earth. So if this was done to scale, the curve for the Earth would be a barely visible blip on this thing. So anyway, so the sun is much hotter than the Earth, obviously, and so it emits radiation at wavelengths that are much smaller than the wavelengths emitted by the Earth. Most of which, again, fall somewhere in the visible spectrum, mostly, or it peaks right around the color yellow. Now, one thing about any system is, in order for the temperature to remain constant, the amount of energy flowing into it must equal the amount of energy flowing out of it. So all of this energy that is being received by the Earth, ultraviolet, visible, and infrared, the amount of energy that the Earth is absorbing must be re-radiated back out into space. If the amount that's being emitted out into space is less than what it's absorbing, then the temperature is going to go up. And if it's emanating more energy than it's receiving, then the temperature will go down. So the reason that the overall temperature of the Earth's surface and in the atmosphere is rising right now must be that the amount of energy that's coming in is out of balance with what's going out. A little bit more lately has been sticking around, so the temperature is going up for that reason. Now, for this to make sense in terms of how the atmosphere works, there are different gases in the atmosphere that absorb electromagnetic radiation. Those would include water vapor, carbon dioxide, ozone, and methane. There's more than those, but I'm going to cover just those. So let's move ahead to the next version of this diagram. Now, what these gray areas represent are the different wavelengths that get absorbed. So, for example, of all the energy coming in from the sun, from about 0.3 micrometers and smaller than that, ozone, and lucky for us, ozone is absorbing pretty much all of the radiation at those wavelengths. Which is good for us because ultraviolet radiation is very dangerous. Anything smaller than visible light, if it can penetrate your skin, which ultraviolet and smaller can do, it damages the cells. So if you're exposed, ozone in this graph, as you can see, not all of it, not all the ultraviolet light, not all the wavelengths, I should say, of ultraviolet are absorbed by ozone. There is some that makes it through. Just before the visible spectrum, and that's the ultraviolet radiation that you need to protect yourself from. This is why you need to wear sunscreen, because if you're exposed to too much UV light for too long, your skin is damaged. We call that a sunburn. So anyway, but luckily the ozone is, and this is up in the stratosphere. This is protecting us from most of it, especially the most dangerous of it, which is at the shorter wavelengths. If it was not being absorbed by the ozone, this is where it would be causing skin cancer, blindness, sterilization. So the fact that ozone is absorbing this radiation on the way in is a really good thing. Now, over on the right side of the range of wavelengths that the sun's light is, when the sun's light gets here, the different wavelengths it can be, over on the right end of it, there are some bands, certain wavelength bands, that are absorbed by water vapor on the way in as well. But what's most important to pay attention to on this is what's happening with the radiation being emitted by the Earth. So if the amount of radiation coming in has to equal the amount of radiation going out without causing a temperature change, then where the radiation is going out is worth paying attention to. So for the Earth, it's somewhere between 4 and 100 micrometers, but mainly peaking between 10 and 15. Now, what's interesting here is from about 14 and up, all that radiation that's trying to make its way out, so the Earth has absorbed radiation from the sun, and any of that that's being radiated back out into space from the surface at 14 micrometers and larger, water vapor is absorbing all of that from 18 micrometers and up. It's absorbing all of it. From 14 to 18, it's absorbing some of it. But from 14 to 18, there's carbon dioxide that is absorbing all of it. So basically from 14 and up, all that radiation is being absorbed by the atmosphere. It's not being allowed to escape into space. On the left side of the Earth's graph, from basically 4 up to 7 or 8, there's a band in there where from about 4.5 to 5, those wavelengths are absorbed by carbon dioxide, and then from about 4.5 up to 7.5 or 8, that's another band that's absorbed mostly by water vapor. There's also a little band just under 10 that is absorbed by methane. It's about 50% absorbed by methane. So methane is also a greenhouse gas that we have to pay attention to. So basically anywhere that is clear, there is no gray, that is where electromagnetic radiation is free to pass through our atmosphere without any absorption. Radiation on the way in is being absorbed at certain wavelengths by ozone and water vapor. Radiation on the way out is being absorbed by water vapor, carbon dioxide, and methane. And other ones as well, but these are the primary ones. So now we as humans are not doing anything to directly add water vapor to the atmosphere. We are adding some methane. Most of the methane we have to worry about being added to the atmosphere actually comes from permafrost, certain parts of the Earth's surface that are currently frozen. As that thaws out, there's potentially a lot of methane trapped in that frozen ground that could be released. The good news about methane is it stays in the atmosphere for about 8 years before it comes back down again. Carbon dioxide, however, is a different story. Once it gets into the atmosphere, it can stay up there for hundreds of years. So it's carbon dioxide that we have to pay attention to, because once we put some up there, for our purposes, it's pretty much up there permanently. So let me highlight just the carbon dioxide bands. So there are 3 ranges of wavelengths that carbon dioxide will absorb. The smallest one is pretty much negligible. It's at the very right side of the graph for what's coming in from the sun. So there's some absorption going on, some sunlight coming in that's being absorbed by CO2 on the way in. There's also some that's absorbed around 4.5, but that's at the far end of what we're receiving from the sun, and it's also on the very low end of what the Earth is emanating back out into space. So that one's pretty negligible. It's the one that ranges that's capturing all of the radiation between 14 micrometers and 18 micrometers, because that's a range of wavelengths that's around the peak of what the Earth is trying to send back out into space. So if we're adding more and more carbon dioxide at a range of wavelengths that represents a lot of energy that the Earth is trying to send back out into space, the more carbon dioxide there is, the more heat is going to be trapped. Now, it's not trapped permanently. It does eventually make it out into space, but think of it as like a stream that let's say there's a stream that has a continuously steady flow at all times. That's not how nature works, but let's just say the stream is continuously steady in how much water is constantly passing by. And you decide to build a dam and to form a little artificial pond. What's going to happen is once the stream has backfilled behind that dam and the pond is full, now the water is going to spill over the dam and continue on downstream at the same exact rate that is coming in from upstream. So again, what's leaving downstream is exactly the same as what's coming in upstream, but there's a whole bunch of it that's stored up in your pond. So that's what the atmosphere does with heat. The amount of heat, without us adding more and more carbon dioxide, which is throwing things off balance, when things are in balance, the amount of energy coming in, again, would equal the amount of energy going out. Otherwise, the temperature is going to go up. And we know the temperature is going up. The average temperature of the Earth's surface, as based on observations from 1951 to 1980, that 30-year average was 57 degrees Fahrenheit. Now it's almost 59 degrees Fahrenheit. It's gone up almost 2 Fahrenheit degrees since that 1951 to 1980 period. Now the goal of the international community is to prevent a 2 degrees Celsius increase from occurring. 1 Celsius degree equals 1.8 degrees Fahrenheit. So a 2 degrees Celsius rise would be a 3.8 degree Fahrenheit rise. But we've already gone up almost 2. So we're more than halfway there. And we're continuing to warm. So we have, and the issue is carbon dioxide, because that is what we are putting into the atmosphere. Now, the thing about the atmosphere, though, when it comes to water vapor, and water vapor captures a whole lot as well, on the way out and on the way in, is the warmer the atmosphere is, the more water vapor there can be. So by us warming the atmosphere by adding carbon dioxide to it, more water vapor can then evaporate from the oceans and exist in the atmosphere as well, and also contribute to a continued warming. Now, but again, carbon dioxide is the important one. At some point, you may have seen a graph that looks like this. If you haven't, what you're looking at is carbon dioxide measurements as measured by what's called parts per million. So for every, in whatever volume of air there is, if there's 1 million molecules in that volume of air, this graph shows how many of them would be carbon dioxide molecules. So back in the late 50s, somebody started measuring the amount of carbon dioxide in the atmosphere at an observatory in Hawaii. And back then, it was under 320. Now, it zigzags up and down each year. There's a seasonal variation because of plants. When the northern hemisphere is experiencing late spring, summer, and fall, when there are leaves on the trees, and there's more land mass in the northern hemisphere than in the southern hemisphere. So during those seasons for the northern hemisphere, when there's a lot of plant life that's absorbing carbon dioxide out of the atmosphere, there's a decreasing effect. During the months when those plants aren't doing that, it goes back up again. So that's why it varies, literally, it's a constant zigzag every single year. But what you can see here is it was underneath 320 back in the late 50s. Now it's up to nearly 420, so it's gone up by nearly almost 33%, gone up by a third in the last 60 plus years. So basically, if you think of each of these greenhouse gases that exist in the atmosphere like a blanket, and carbon dioxide is one of those blankets, we're making that blanket constantly thicker. I mean, when you're cold, what's going on is your body temperature, the heat from your body is escaping into the air. If you're wearing clothes that aren't warm enough or aren't thick enough to keep you warm, you're warming up your clothes. The clothes are then warming up the air, and heat is escaping into the air at a faster rate than you can replace it from your body heat going back into the clothing. So you put on a blanket, and the blanket then slows down your body heat escaping out of your clothes and out into the air. The thicker the blanket, the more your body heat is insulated from getting away. Now, when you put on a blanket, the blanket doesn't generate heat itself. It's not a source of heat. It's just re-radiating back towards you your own body heat. And that's what carbon dioxide does. So the more carbon dioxide we're adding, the thicker we're making the blanket for hundreds of years, because that's how long that stuff's going to stay up there. And so then you end up with something like this. Now, this was something that was just released within the past couple of weeks by the National Oceanic and Atmospheric Administration. This is the annual mean temperature change across the United States. So climatological averages are based on 30-year averages. So the 30-year average taken from 1981 to 2010 was one set of numbers. Then if you take the average temperatures from 1991 to 2020 and subtract the averages of the previous period, you get this graph. And this shows that in certain parts of the country, there's been barely any warming at all. That would be in the Dakotas and a little bit of Montana. But otherwise, the entire U.S. shows a range of warming up to 1.5 degrees or more. So now this isn't like a one-time thing where it has warmed and now it's going to stop warming. This is just, the warming is probably going to accelerate. That's what makes this so dangerous, because we know the source of the warming is all of the carbon dioxide that we keep cranking up into the atmosphere, and it's having secondary impacts of allowing more water vapor to get into the air. It's melting areas of land that have methane trapped. So now that methane is being released, that's a greenhouse gas. And you get this, what's called a positive feedback loop, where the more carbon dioxide we add, the more other gases end up being added by nature, which then in turn allows even more to be added, and then even more to be added, and so on. We are just at the beginning of this. This is going to go on for hundreds of years. So now how bad it gets between now and hundreds of years from now, this is in our hands. So that's why it's so important, I think, to first understand what climate change is, so you can understand the things when people are talking about what can be done about it. What you really need to understand is, in the short term, it comes down to cutting down on the emissions of carbon dioxide as much as possible. Or every 10 years, this graph is going to be more and more red, because the temperature increases, the temperature changes are going to be more and more drastic. So this is where we are today in terms of how much the climate has already changed, how much it continues to change, and the cause is how much carbon dioxide we're sending up there. Again, the point of this channel is I'm assuming that the climate is going to change. I'm assuming that there's not really a whole lot we can do to prevent a whole lot more warming from occurring, warming that will eventually raise the ocean levels, not by inches, by feet, and likely double digits, up to 20 feet. Now, it may take hundreds of years. We need to start planning for that right now. So anyway, I'll wrap this one up here. I hope you enjoyed it. If you did, please click like below. Please comment as well if you have anything to say or any questions. Please do subscribe, and I'll see you next time.